Then we put this 12-bit single DAC cell together with 16 others. Yeah, so these are 16 cells. And then you see that it's very compact, rectangular shape, so that integration is enabled. But in the measurements, of course, this is a test chip. In the measurements, we couldn't really measure the full potential of such an array because we are limited with the initial problems of how to get digital data for 16 D to A converters and how to get in a more flexible way their output and combine it together depending on the application, of course. So for our measurements, what we did is that we measured a single DAC cell performance and also, as an illustration, a combination between two DAC cells used together as a single 13-bit DAC. What does this mean is illustrated here with this INL. So you see here the pattern of a single DAC cell, and we stack on top of it the other. You see that they're different D2A converters, even though they are adjacent to each other, and their gain errors are different, and their pattern here in the binary current errors are different. However, if we run the calibration, they're aligned. So yeah, in real life it will not be used like this, but this is just to illustrate the big mismatches that exist between DAC cells and how the calibration can help. Then this is a measurement of SFDR, spurious-free dynamic range. 1 gigasample per second, so the Nyquist band is from 0 to 500 megahertz. And what we have here is just the performance of a single 12-bit cell and this combination of two stacked D2A converters to create a virtual 13-bit DAC. So what you see here is before calibration and after calibration. So before calibration, you see that the 13-bit mode is even worse than 12-bit, and this is because of the large gain errors. However, when we calibrate both, the performance is improved by about 8 dB. This performance is kept up to 50 megahertz, and beyond that dynamic errors start to kick in, so the performance decreases, and it again stabilizes to a level of around 50 dB, 55 dB at high frequencies. So this is the sweep of AMD3. Again, what we see here at low frequency, the performance without the performance before calibration is about 10 dB lower than the performance after calibration. When we calibrate, the AMD3 improves, and then then these advantages are kept to about 100 megahertz. After that, as the timing errors and dynamic errors become dominant, the advantages of the static calibration are lost. So here are some spectra to see. This is at central frequency of 80 megahertz and spacing between the two tones of 1 megahertz. So here we will measure AMD3, and then before calibration we have about 72 for this particular point, and when we run calibration there is a 10 dB difference improvement. See how clean the spectrum is after calibration. So this is at 80 gigahertz, and if we push this to 350, which is kind of big performance for this D2A converter, we can measure AMD3 of about 60 dB, around 350 megahertz. Then to compare with literature, I have this table. So our goals for this design to enable, for example, massive arrays for 5G, for digital beamforming, we need small area because we want massive arrays integrated in a single chip. We want wide bandwidth and high linearity because these are for telecom, for wireless communication. Then this is, of course, as shown, enabled by the calibration, and the calibration actually allows us first to use large binary segmentation part, which makes the whole architecture of the D2A converter very efficient in both resources, area, and power consumption. And so this is one. And the second thing is that the calibration allows us to design very small transistors, arrays of current sources, which will feature unavoidably large intrinsic matching errors, and the calibration will improve this. And this leads us to this very small area. If we look with the others, what the others are doing, we'll immediately spot this D2A converter, so published 2019. However, if we look closely, you see the performance here. And the reason is that this is oversampled DAC. So this is digital sigma delta, and which uses high oversampling ratio, and this results into a very small bandwidth. If you look at some recent publications in a very advanced technology such as 16 nanometers with amazing performance, still the area that is needed is about 10 times bigger than ours. And this is even though the difference in the technologies, 16 nanometer versus 40 nanometer, but effectively implemented at 250 TOPS. And the major difference, of course, is the choices about the architecture. So our binary architectures, and the calibration, of course. So in conclusions, let me briefly repeat that binary DAC architectures are efficient in terms of both power and area. Then calibration of errors, however, is necessary to compensate for their deficiencies, and calibration enables binary architectures with our algorithm for binary current calibration, and it also allows small current source arrays, which reduce the size of the DAC cell enormously. Then massive integration will become possible, but further validation is needed. We integrated 16 D2A converters, but we couldn't really measure these so far in a phased array setup. This is work for the future. And here are the references that were used in my presentation. Thank you very much for your attention. Bye.